We looked in some detail as to what a CNN is and how it is put together. Now, let's look at some aspects related to CNN training. Training is the process of running training examples through our model from first layer to last to make a prediction, and then figuring out how wrong we were. We next back propagate this error through our model in reverse order, from last layer to first, attributing blame for this error to each of the weights we meet along the way. We use back propagation to adjust the weights slightly with the aim of predicting better the next time, i.e. reducing our prediction error. We do this for all our training examples. This is called one epoch of training. We then repeat until we meet a certain level of accuracy or until we've trained for a certain number of epochs. Gradient descent is an optimization algorithm used to find the parameters or weights of the network that minimizes its error or cost function. We start off with random but non-zero values for the weights and pass our labeled training examples through the network. Then we evaluate the error. We calculate the derivative of this, which is the slope of the function at that point if you're familiar with calculus. With the derivative, we can adjust the parameters to get a lower cost for the next iteration. Our learning rate parameter, alpha, is used as a brake to slow us down. We only apply a certain amount of the derivative each step. We don't want to go too fast, because we'll end up shooting past the minimum and perhaps over to some higher cost region. Our network might fail to converge, or worse, it could actually diverge. Likewise, we don't want to go too slow, because training will take forever. So the learning rate is an important parameter to tweak. We could train with all our examples at one time. This is regular batch gradient descent. We could also train one example at a time. This is called stochastic gradient descent. Or we could train our solution in mini batches. With mini batching, we split our training data into smaller chunks, called mini batches, and train on those instead, one at a time. Using mini batches has a number of advantages over single example at a time or over single batch at a time. Versus one at a time, it is more efficient for parallel implementation. Our GPUs can operate on all of the examples in our mini batches in parallel, greatly speeding up our training time. It uses less peak memory than a single all-at-once approach, and allows us to use much larger training sets and have them fit in our GPU memories, again speeding up training. Finally, it acts as a source of noise and helps us escape from being trapped in any local minima or saddle points during training. With mini batches, once all training examples have been processed across a set of batches, this is considered one epoch. Note that using mini batching does require that inference error information is accumulated across the entire epoch before doing backpropagation. Mini batches also give us the opportunity to do batch normalization. Training deep networks is complicated by the fact that the distribution of each layer's inputs changes during training, as the parameters of the previous layer will change. This slows down training and makes it more error-prone. It was discovered that we can normalize layer inputs as part of the model for each training mini-batch. That is, at multiple points throughout our model, we can normalize the inputs to the next layer, centering them on the mean and adjusting their variance to standard deviation. This helps keep our error gradients strong and allows us to use higher learning rates. It can also act as a regularizer and helps us prevent overfitting. The learning rate is a parameter of the model that helps decide how much of a step we take for each iteration of gradient descent. Choosing a proper learning rate can be difficult. A learning rate that is too small can lead to painfully slow convergence. It will result in small baby steps towards finding parameter values which minimize loss. Conversely, a learning rate that is too large can actually hinder convergence and can cause the loss function to fluctuate around the minimum or even to diverge. Should the same learning rate apply to all parameter updates? If our data is sparse and our features have very different frequencies, we may not want to update all of them to the same extent, but to perform a larger update for some rarely occurring features. We've shown our error function earlier to be in the shape of a bowl, but our multi-dimensional surface is highly likely in practice to be much more complex, much more noisy and bumpy than this. A key challenge of minimizing error functions for neural networks, therefore, is to avoid getting trapped in their numerous suboptimal local minima. Difficulties arise not just from local minima, but also from what are called saddle points, points on the surface where one dimension slopes up and another slopes down. Thus, the overall gradient appears to be zero, but we're not even at a minimum. These saddle points can be surrounded by a plateau of the same error, which makes it difficult for regular gradient descent to escape, as the gradient is close to zero in all dimensions. One solution to this is to use what is called momentum when learning. The momentum algorithm accelerates gradient descent by keeping an exponentially decaying moving average of past gradients, and it continues to move in the direction suggested by that average. You can think of momentum as being akin to throwing something down a hill, and the way it gathers momentum and speed, which it then uses to carry it over small bumps and perturbations along the way. Momentum not only helps with saddle points, but also with high variance oscillations in gradient descent that can make it difficult to achieve convergence. When performing gradient descent, the learning rate determines how much our current situation affects the next steps we take. Momentum determines how much past steps affect this next step we take. In addition to momentum, there are suites of different learning rate optimizer algorithms. We'll mention ADAM here because you're likely to see it in the code for our later labs. ADAM stands for Adaptive Movement Estimator. It is another method that computes adaptive learning rates, this time for each parameter of our network. It works well and is a very popular choice for learning rate optimization as it helps networks converge quickly. We've introduced a lot of theory here. We've covered convolutional neural networks, how they encode spatial information in their structure, and consequently have been very successful in achieving huge accuracy in a variety of image-related applications. We've looked at how they are constructed from many layers of convolutions, nonlinear activation functions, and pooling layers, often with fully connected dense layers at the end. We've looked at how ReLU is a common activation function in the hidden layers, and how softmax is commonly used in the output layer. We've discussed how training involves back-propagating errors, assigning blame for them to individual weights and making small adjustments to those weights in order to make a better prediction the next time. We've also discussed gradient descent and learned how training has hyperparameters associated with it, such as mini-batch size, learning rate, etc. We looked at batch normalization and how it can help improve training and convergence. Finally, we briefly discussed learning rate optimizers like momentum and ADAM, and how they can help us reach convergence and avoid high variation and saddle points in our error surface. Hi again. In the next lesson, we'll look at some of the more famous CNN architectures for image detection.